Okay, good afternoon, everyone, or morning, or whatever it is in your time zone. It's just afternoon for me. My name's Steve Downey. I'm a software engineer at Bloomberg, where I'm currently working in the system reliability engineering group for what we call the communication channels group, which is responsible for our customer-facing email and instant messaging systems that our customers use to communicate with each other, do activities like trading, um, etc. Uh, I've been active with the C++ standardization and efforts for several years now, since about 2018 in San Diego. One of the first pieces that I got involved in was modules, and in particular, the fact that um, the physical model for modules is going to be very painful for adoption. And I believe this is still the case. We'll be getting to some of the issues why as we go through this. Um, However, I still have a lot of hope for modules. I think they can have a good chance of improving the, the language and improving libraries. So what we're going to be discussing is writing a C++ 20 module, taking some existing code uh, and modulating it. So I'm going to walk through creating a C++ 20 module interface. We're going to be implementing, or actually taking the implementation of a data structure I already have, a functional tree. We'll be covering how to export the types necessary for the customers of the module, code to inline, hiding implementations, and making sure that anything that's not exported is still reachable. A quick, possibly not so quick, overview of C++ 20 modules. The first thing to understand is they're not packages. It's about hygiene, about what things are visible. In the run-up to C++ 20, there was a lot of hope that modules solved packaging. Packaging is a huge problem for C++. Modules sound like a name that relates to packaging, but they don't at all. In fact, they add to the problem. One of the big problems is you're going to need to deliver source for interfaces that consumers are going to compile. There's no good solution for delivering a binary module interfaces, except in extremely tightly controlled circumstances. Um, the compilers essentially have internal state that they dump into the binary module or a compiled module interface, and they just suck it back in, which means that every version of every compiler is probably going to need different instances of the compiled interface. We don't know how to ship these yet. Let's talk about module units. Essentially, modules extend the concept of a translation unit, the fundamental unit that we've always worked with in C++. A module unit is a translation unit that contains a module declaration. Named modules are the collection of module units, module names. Module interface unit is a module unit that exports. A module implementation unit, a module unit that does not export anything. The primary module interface unit, there's going to be exactly one module interface unit that exports everything that anything else can see, and that's not a partition. And you have module partitions, which is a way of breaking up modules into parts. That's a lot of terminology. Go over it a little bit more in depth. This is an example from the international standard. We've got translation unit 1, a primary module interface. It's going to export module A. It takes a module partition foo, imports it and exports it again, making it available for clients of the module, and exports the declaration of the function baz. Translation unit 2, partition a:\foo. So we export module a:\foo. We're going to import the internals partition, and we export a function foo, which uses the function bar that comes from the internal partition, which is not exported anywhere. So we have a module A internals, which exports the declaration of bar. And then we have a translation unit, which is an implementation unit, which is module A. It imports the internals interface and provides definitions for bar and baz. You can see here, so basically we can control which parts of our module are visible to clients. We can export forward declarations or just declarations. We can export definitions. We have a lot of control over what we want to see exported to clients. Essentially, the model is retrofitting existing tech. The standard's complicated because it's trying not to describe an implementation. When you read through the standard, it can be very confusing about what's happening where and why. But essentially, a module interface translation unit, the primer, produces an object file because it's a translation unit, and a binary module interface. A module translation unit is a translation unit. That's why it produces just an object file. The consumer of a module reads the binary module interface, and a program will links either the library or objects from the module. At a physical layer, it's not, there are a few parts, but they fit together in fairly natural ways. This isn't, at the physical layer, there's no particular magic. When you import something, you're grabbing the contents of an already partly translated file. So which is where the efficiency comes in. The front end has to do far less work in bringing in a module interface. Now, export make names available from the module available to consumers. Reachability, which we'll get to, is also allows things. We can also actually export particular implementations. Inline keyword comes into play. The other thing that comes up occasionally is that there are certain ways that customers, clients of the module, can use the types that are not exported. For example, you might use decl type to see what use the return type of an unexported function. But essentially, export is about making names available. Okay, import makes names from the module visible in the current translation unit. We have something like export import m, which will take which will import the module and then re-export it to the importer of whatever module we're defining. So We can transitively make available names that appear to be from our module interface from some other module. We also have the private module fragment. You can write Java-style single-file modules, essentially defining everything in your single translation unit, compiling it out to an interface and an object file um, in one single file. Declare the fragment by using the module :private. The names and definitions after that point are not going to be reachable for the importers. Yeah. When we're looking at what importers do, we have to consider the instantiation context of things like templates. Templates are instantiated, roughly speaking, where they are used. Pretty much the way we do now. However, you can hide more of a template than you can with a header file. So basically, the instantiation context is where we figure out what declarations in play for ADL and which are reachable. So, reachability is an important context. Reachable isn't the same as name availability. The standard basically flat out says whether a declaration is exported has no bearing on whether it is reachable. So this comes up, for example, we can return a type by value without making that type itself available for or use by customers. It's like, so they might only be able to pass it to something else without doing anything like make a copy of it. The translation unit is reachable from some point P, the unit P, and it has an interface dependency on U, the other translation unit. If the unit P is in imports U, P being the point we're looking at, and other unspecified reasons you should not depend on. And that's a quote from the standard, which is a little disappointing, but it basically means compilers are obliged to make things reachable. They may occasionally make things reachable just because, and you should not depend on that. Declaration is reachable from a point P if it appears before P in the same translation unit, which is just what you would expect today. And if it is not discarded, it's in a unit reachable from P, not in the private module fragment. So basically, if we're looking into a module interface, we can reach further into the things that are declared there that may be used in definitions that are exported. So for more concrete example, we have translation unit 1. We're exporting module A. This is the module interface unit for A. We have a struct X, empty, and we export a using declaration of Y. So we have export using Y equal X. In translation unit 2, in module B, we import A. We can declare an instance of Y, which depends entirely on X. It is an X. But the name X isn't visible, so we could not actually declare a variable of type X, even though we can declare a variable of type Y, which is an X. critical thing to understand is essentially that reachability is ABI. Export is making names available. Reachability is your what the clients of the module can really depend on. Okay, let's talk a little bit about the component that I'm going to be modulating, modularizing, however you want to say this. What I have is an existing component called fringe tree. Fringe tree is a pure persistent functional tree. It's intentionally a poor one. I was writing it, exploring the use of a variant, converting various functional components that use pattern matching in their natural habitat, seeing how that can be translated to visitor, wanting some examples to work with coroutines where the same fringe problem comes up for this kind of structure. Essentially, a fringe tree is one that stores all its data in the leaves, and in the internal branches have no data associated with it. So the question often comes up: are two are these two fringe trees equivalent? That is, are the leaves iterated in the same order, even though their internal structure of branches may be quite different? Um, Persistent in this context means that we don't modify the tree. If we insert into the tree uh, I hope uh, that the doesn't change the tree that we're working with. It it produces a new tree. However, the new tree can share state with the old tree because the data structure is immutable. This is modeled after finger trees, which are a much more complex and interesting data structure. Uh, They share the same API, but the internal structure of this thing is just essentially a binary tree. It uses standard variant, standard shared pointers and visitors. Um, Shared pointer isn't a particular problem delivering to customers. However, just including variant is very expensive. It's uh, not cheap to compile, introduces a lot of overhead and everything. Stud variant visitors are also somewhat complicated to deal with into template instantiations. Um, the actual interface of the tree doesn't need to expose variant or visitors at all, other than it accepts a visitor object to iterate over. So essentially, this is a poster child for modules in the sense that um, there's implementation that customers don't need at all to use it, but templates right now mean that they're forced to. Okay, if we take a look at I'll show the code in a minute. There's a template parameter value the type of data that's held in the fringe, the template parameter tag, monoidal type that describes the tree. The nodes of the tree are one of a branch, a leaf, uh, empty, and then there's tree that holds uh, either a branch, a leaf, or an empty as a variant. So branch simply just has a tag for the branch and shared pointers to tree for its left and right. Leaf has a tag and a value. Empty has nothing. I'm using empty as the nil value instead of having to deal with null pointers. uh, simplifies some of the code in checking, in matching patterns. The tree itself holds in its data a variant of empty, leaf, and branch. We can construct a tree over either over an empty or a leaf or a branch, where those are actually type defs to the template expansion for the empty, leaf, and branch. Um, it The core operation on a tree is taking some callable object and visiting the callable over the data. So the callable will have uh, operators for function call operators for either an empty, a leaf, or a branch. Operations on trees produce trees that share nodes with the original. Also, tree exposes factory functions that return the shared pointer of tree while constructing an empty, a leaf, or a branch. This is a smart constructor idiom. Uh, One of the pieces from the overall pattern, tag. Uh, a branch is the plus operator of the tags of its left and right. The tag type's monoidal, that is, it must have a binary operator that takes two tags, returns a tag, has an identity element such that tag plus identity is identical to the original tag. Um, Such things are like the plus operator on numbers, typical one, concatenation of strings or other linear containers, lists, vectors. Min and max are also monoidal operations. Um, for uh, for the tree, we can end up using the standard plus operator to help define index operations, where the index tells you about the um, uh, where things are in a tree and insertion and tag order. We can use min or max to define priority trees. There's a fairly well developed theory about these things. I was mostly interested in it because it was just interesting. Um, Now, the general pattern that Fringe Tree uses exposes function objects as its interface. I was playing with nebuloids early on here. Um, so we'll have a struct depth that is our visitor object, uh, which looks at either empty, leaf, or branch. The depth of an empty tree is 0. The depth of a leaf is 1. Depth of a branch is the sum of its left and right uh, depths. So we just recurse down the tree, and we provide a Constexberg depth object, a lambda that calls tree visit with the depth that we've just defined. More complicated one, flattening to a vector, which is useful in testing. So we can compare that we've constructed two trees that result in the same set of fringe. This is I wrote this because I wanted it before I got to the point of being able to iterate these to be able to see that I was writing tests correctly. Uh, so some example code. We have uh, there was a using declaration before here. This tree is a tree over int and int. We construct a branch over a branch over two leaves and another leaf. There are operations prepend and append, which take a value and stick it on either before or after the entire tree. And then have some printers, which essentially print things out in GraphViz dot notation. So we can take a look at the resulting tree, and it'll look something like this. So we've got the top level little branch that points to a branch on the left and a value on the right. And then we have the branch on the left that points to two leaves, which have value 1 and 2. Here we're just adding up the tags to get the value. The total output from the example looks like this, where GraphViz has coalesced the particular instances of the nodes. I haven't coalesced the shared pointers. So this essentially is overlaying a few different trees. But you can see from this that the trees share the nodes where they can. So when we append a tree, append a value to a tree, we create a new tree that just has that the additional new parent nodes that are necessary for it, and reuses the existing nodes which aren't being changed. The most important thing about this, it's an experimental toy. You can go take a look at it. Don't put this in production. It's very much a use. It's very much just in use for experimenting for things like this with C++ features. One of the most important things that came out of this for me was that we really need pattern matching to be able to take modern algorithm research, which is very often heavily defined in terms of pattern matching, because it's fairly painful to write the visitors out when you know that you're just trying to match a pattern. On the other hand, the other important result was that I could take these existing algorithms and model them using standard types. Variant and visit that can model some type system that works correctly. Okay, now considerations for a module. Like, we're taking something existing, and everyone's going to have a lot of existing code, and we're going to want to figure out how to put it into a module, or building a module from scratch where we have the same sorts of questions. Now, these aren't new decisions, but we have a lot more control than we do with existing template and templates and headers. Export, you have very fine-grained control. You can choose everything, which is simple, and essentially gives you what you would have now in a header, only you only have to compile it once and can use it. Or you have more fine-grained control. You can export just particular names and provide make particular definitions reachable. What you want to export are things that clients need to name. By need, you want to provide some sort of convenience. I'll get to a concrete example in a moment. What not to export, you don't want to export your implementation details or your infrastructure. Or at least initially. There are always trade-offs. If you don't export your implementation details or the infrastructure for them, you may lose optimization opportunities. Or you guess wrong, and it turns out that or clients really do want to use that uh, aspect of your code, and you've made it unavailable to them. Um, this comes up fairly often in writing tests, that something that you don't consider part of the interface for your module, but it turns out you want to use it in your tests, um, which means that if you've written your test uh, outside the module, you need to export that if you want to use some of that to be able to check on things. Um, there's, of course, a lot of ongoing discussion and decisions to be made around here. I tend to fall on the side that if I want to use something in my tests, other people using my components probably will want to use those same things, if just to be able to sanity check or assert. One key question is exporting code for inlining. If you want your code to be inlined as part of your interface, you must be explicit about that. Uh, Functions defined in a class declaration in a module are not implicitly inline in a module. Um, uh, the other key thing is inlines can't refer to anything with internal linkage, because they how would that work? Although we did try and figure out a way to make that work. There was early on a feature called linkage promotion, where if your exported thing had a referred to something that had internal linkage, we try and promote that to module linkage. No one could get it to work, and the standard wording was terrible. So we just have a rule: you can't do that. It does mean, though, you have more work to do um, if you do want to inline, actually inline in your client's code, your simple functions. So we've got basically questions about optimization and what you want to make available. Um, This is a distinct change from templates, where they're in the header file. So therefore, your definition is inline because it has to be. You now have you now have more choices to make. Um, this is this can be very good for fairly complicated functions that you never really wanted to have inlined, nor did you to want people to depend on them. Um, Another thing is that your organization of your module is not exposed to customers. So you can use partitions, private module fragment, module implementation units. These all look the same to your customers. They're um, not part of your binary interface. So you can then reorganize your code later if you uh, decide that your organization is not exactly what you want. However, caveat, uh, re-exporting a name from a different module uh, may be visible. Uh, Names are attached to modules, and that attachment may be part of the name. This is the strong versus weak module decision. Um, the models are different. Microsoft is using the strong model, uh, which means that they have the ability to detect uh, one definition rule violations. If two things are exported from different modules, they can identify that they conflict and where they're coming from and prevent all sorts of errors. Um, on the other hand, GCC and Clang are using the weak ownership model, which means we have more flexibility in, for example, mixing modular and non-modular code. Uh, we could just link in .os that are from a module into our non-modular code that we might expose through a header file. There are trade-offs on this on both sides. It's probably not worth worrying about too much, since it's not something that, as a working programmer, you have any control over. It's more something to realize that this may happen to you and confuse you or your colleagues. Okay, so let's hello world. This is a very simple hello module. We have actually, I haven't mentioned this before. The initial piece here is the global module fragment, where we can do things like include or otherwise define things that are not part of our module and not attached to our module. So we can include IOStream, we can include string view. We're going to export the module smd.hello, where smd is me. We're going to export the namespace hello, which exports everything declared within that namespace. And we writing a simple function that takes a string view and counts it. The namespace does not have to match with your module name. This is all mix and match. You probably want to make sensible choices here where your names will be at least related, or you will end up confusing yourself because you have things coming in from various different namespaces, and it'll be very easy to lose track of where things are coming from. This is not particularly different than header file naming, however. So we can have in our main, we're going to import the SMD hello module, and from there I can now just call hello with my name, and that will produce the results. Run the program, it'll print hello Steve out to the console. We can, I have a working makefile for this, which was a bit of a challenge. I'm using here GCC 11, and this actually works with GCC 11. Our main program depends on the two objects that we're building, the object that comes from main itself and from the module translation unit where we're defining the function. What I'm doing here, I am depending on the GCM, which is the binary artifact that GCC produces for translating a module interface. That's its compiled module interface or binary module interface, CMI or BMI. We're compiling with the modules TS option, saying this is a C++ program. I'm saying that the interface depends on the object file, and first do is test that the file exists, remove the file, the object file, and then remake it. This is a fairly standard pattern in Makefile, particularly Gmake, when you have a process compilation which produces two outputs. GCC doesn't have a way to not produce the BMI when you compile to the object file. So we need to be able to handle that. Then I have various clean targets, making sure that the dependencies work, and a test target that actually runs this. This works today with GCC 11. However, we'll say there are a lot of outstanding bugs. If you go to GCC's bug database, Bugzilla, look for modules, there are many internal compiler errors, segmentation faults, etc. I ran into a lot of these, and it's painful right now, but rapidly improving. Okay, so let's take a look at the code that would use for defining modules. We have a primary module interface. We have the global module fragment where we can have declarations that aren't part of the module. That's where you can pull in your non-modular code, stuff you can't import. This is basically what a primary module interface is always going to roughly look like. So we can we export our module foo. We're going to import a module partition and export it again. We're going to import stud. Compilers are mostly modularizing the standard library as one large module right now, at least for experimental purposes. We really hope to be able to define better standard modules so you don't actually have to import the entire standard. Microsoft has some code in their current preview, which exports a few different module and submodules from standards, such as standard core, standard IO, etc. We've also mandated that standard headers should be importable. We don't actually have full existence proofs that this works yet, primarily because the existing standard libraries rely on C standard headers, which often do things like export the same name from different points, depending on various pound defines. And that makes it fairly complicated to modularize them just as such. Now we can import bar, some other module, which we're not exporting, but that the parts of bar that we use would then be reachable. And we export our answer, and everything inside that export namespace is transitively exported because we're exporting that namespace. And we declare a function, the answer. Now, one thing that's useful to know is that modules compose. So we could export module foo that's made up of foo.bar, foo.baz, foo.cooks. And this can works as long as there's a strict directed acyclic graph between the more fine-grained modules. Note the dot is a convention. There's no hierarchical meaning to the compiler. But there are reasonable mappings for dot to the file system, either just in the file name or this could be in directories. We expect a lot of experimentation over how to organize modules in the coming year or two or more. I'm sure we'll all come to broad agreement the same way that we've come to exactly one way to lay out our source code in everyone's project. That's sarcasm. Okay, module implementation units are pretty much the same thing as a regular translation unit, only they have access to anything with module linkage. Declare that this translation unit is part of module foo. It's not exporting anything, and here's our definition for the answer 42, the standard answer to life, the universe, and everything. This would compile into a .o. It wouldn't contribute to any of the interface, any of the compiled interfaces, and you would just need to link that, either add this .o into the library or link the .o into your larger program, just like any other translation unit. Now, module partitions, useful for decomposing larger modules. If your modules are large and you don't want to decompose them into individual modules. So we export module foo part and export a declaration quux the foos, taking an int. The important thing about the module partition is that no one outside the module can import. You can't from elsewhere import just the partition. You can't import foo part. So you're isolated, and your organization is insulated from the outside world. The important thing, you have access to names with module linkage, your module partitions, you have all the names and different definitions from the module interface. In what I have done so far, I have not actually made a single module that's large enough that I've really wanted to use partitions. Partitions are also much more complicated in terms of implementation of my code, and this is also an area where even the Microsoft compiler still has open issues, where the Microsoft compiler is the most advanced in the with their module implementation. The other tool you can use for organizing your module, the private module fragment. And I'm pulling this example right from the standard so I can point at the various things that we want to talk about. So we're exporting module A. We're going to inline the inline void function E. We also have a inline void function M and a static void function S. We're exporting the struct X without a definition. One important thing I don't actually haven't mentioned it. The export needs to be applied at the first point of declaration. This is going to be troublesome in converting code to modules. You won't be able to just pound include my thing and then export parts from it, which I'd originally hoped we could do. But compilers need to know what things are exported in order to understand subsequent code. So here we're exporting struct X without providing a definition for it, and exporting a function G that takes an X pointer since we don't need a definition in order to use a pointer to a type, um, we can call from this function a static function in the same translation unit, and we can call that module linkage inline function. Uh, those are both fine. And we can export a factory function. Now, the private module fragment lets us then provide the definition of struct X, which will not be reachable for importers of A. That means that even though it's appearing here textually in the module, someone couldn't write a decal type star X of whatever factory uh, and declare a variable that way, or use the return type of factory and manage to bootstrap that into a instantiation of X. There are lots of metaprogramming tools now for being able to work with things that you don't actually have names of. But since it's not reachable, they won't be able to do that. So here in the private module fragment, we have our unreachable definition of X, we have the definition of the factory function, and we have the actual definitions of all the functions that we've mentioned so far. So this is a tool that's probably going to show up in teaching because it's concise and contained. I'm not convinced that it's the right thing to do in general. Mixing implementation and interface, particularly changes in your implementation, are likely to force recompilation broadly. So, however, the C++ standard tries to avoid policy for this sort of thing. Lots of people want single file modules. They've always wanted single file translation units. We certainly uh, have been using header only components and header only libraries to good advantages. Certainly, it helps solve the packaging problem. We don't have with a header only library, you don't need to sort out compilation flags, etc. With a single file module, we'll have to sort out flags. There will have to be consistency between whatever is using the module and the translation of the module. But it's still going to be much easier to pull them into a project. However, it's going to make build systems more complicated. We're going to have most likely rebuilds of anything that depends on your module, even though you've only changed the implementation, something in the private module fragment, at least barring a mythical smart enough build systems. And build systems just aren't that smart. I've done too much work on them. Okay, let's talk a little bit about building modules. Your current build system is not going to survive contact. We've known this for years now. The various meta build systems are all actively working on this problem. Build 2 has one solution that is out there now. Everyone else is keeping up and plans to have good support for these. The biggest challenge is the name of a module in code is not a file name. So figuring out module dependencies requires parsing of C++, which is hard. Standard tries to make it pretty much regexable. That is, you'll be able to mostly grep. Um, Module isn't allowed to appear. Your module declaration isn't allowed to appear inside macros directly after certain kinds of macros, etc. But it's still very complicated. The other big issue is you have to build in the DAG order. Before a module can be imported, it has to be built. If you're lucky, if you get this wrong, it'll be built in the wrong order and the module interface won't be available. Otherwise, you'll be unlucky and you'll have a stale module interface and things will seem to work, but will still be wrong. This will manifest in various things. I changed that, but why doesn't the importer see the new definition? It should have broken. And then you'll compile again and now it will work. Basically, we're going to go back to the future. So we have a very long time ago, before current dependency technology was invented or implemented, the program make deps. Currently, a compiler emits dependency information as a side effect of compiling. This works because if we don't have the if we're going through the first time and don't have dependency information, we can assume that we need to compile it. So we compile it and get the dependency information next time. And then from that point forward, the only way that the dependencies can change is if the text of the dependent files changes. So we just check the timestamps and rebuild, causing the recompile, getting the new dependency information. Before we got compilers to do this, there was a tool, makedeps, which would run before your build, updating all the dependency information so that your compilation could happen. This was 20 years ago, unbearably slow. It's actually not that slow today. File systems have gotten a lot faster. Computers have gotten a lot faster. Dependency scanning has gotten a lot faster. This is sort of like the difference between using traditional grep and, say, ripgrep, where the first time I used ripgrep, I thought it was broken because it happened too fast. But we basically need to run makedeps before the main build, update our dependencies, possibly rework the dependency graph in order to fit any changes in, because you might have said in one of your files, import something, and now this pushes that file ahead of its new dependency in the graph, or behind it, however you want to look at it. Compiler vendors are working on tools to admit what modules are direct dependencies of a particular translation unit. And if you have the direct dependencies, you can build up your graph of your indirect dependencies. We also need to know what module a translation unit produces. And with those two things, we can tie together what we're doing. And basically, that's what I was doing by hand in the makefile that I was showing before. Doing it by hand, of course, does not scale. And we need this to scale, especially everyone has gotten used to incremental builds that just work. At this point, if you need to make clean, your build system's broken in some way. Your incremental build should always produce the same thing as what your clean build produces. And we want to maintain that. Other things to consider, packaging modules. That's an open question. We have no good solution for this right now. We might be able to extend package config metadata to indicate what are module dependencies. However, at this point, there's divergence in compiler flags. So explaining how to use a module correctly is slightly open. Hopefully, as we get modules actually working, we can restart the work with the tooling study group and get some consistency or at least metadata that we can share. Another big issue is that compiled module interfaces are fragile. Plan on delivering source. You, you will not be able to ship your compiled module interface. That compiled module interface depends on compiler internals. Now, I might be able to internally at work. Basically, we version our compiler along with the libraries and packages. What we ship out internally is basically an OS distro with just userland about every 15 minutes. So when promotes a package, we rebuild what's necessary and make that one available very quickly. We have a lot of CPU devoted to making this happen, though. But it does mean we have consistency with everything that we're producing, so we can ship binary artifacts to each other safely. Okay, so let's take a look at some actual modulation. The code I was showing earlier. Heads up, this was successful with Visual Studio Preview Edition yesterday. I finally got everything that I wanted working. I iced GCC. At certain points, I got actual seg faults in the error report, reporting the errors in the compilation. So yeah, this is bleeding edge stuff for even in GCC 11 with module support. Clang was somewhere in between. I didn't get internal compiler errors, but I was seeing certain reachability issues. Code that I should have been reachable wasn't. It's possible I could have made this to work, but I stopped. The actual work, once I was using Visual Studio, was actually fairly straightforward. This possibly partly because I'm in the habit of building Lacosian components, so I already have strict DAG order, well-defined dependencies, and tests are always part of any particular component. Convincing Visual Studio to export the interface a little more frustrating. I'll admit I'm not a fan of GUIs for this. Directions where it would simply open the X dialog, not particularly simple always, but it worked. Okay, basically, Visual Studio uses a new file extension, IXX, for their interface C++. I don't know what our eventual style guide is going to be here, but essentially I was able to just take the header file and start off by prepending, moving it to IXX, starting with the global module fragment and including the standard headers that I need. Then I exported module smd.fringe tree. I'm going to claim the SMD module space. Go find your own. This is equivalent to the namespace problem for shipping code around. Your component probably has a nice common name. You need to find some way of namespacing things. We don't have a way of namespacing module names that aren't just part of the module name. So, okay, then we export the module fringe tree, and I'm decided not to export the entire namespace, although I did for the first time and that worked, which was good. I wanted to see how I could have more fine-grained control. When it ended up doing, exporting the tree type, where the node types are just reachable. So we have I'm exporting the tree template, making that available. I didn't export leaf, branch, or empty. At least in my tests and my code, I didn't have cases where I needed to use that type other than via the shared pointers that were coming out of the tree. So for example, I'd want to be tree itself. I want to export, frequently want to give a particular template instantiation of the fringe tree a name, like for example, using tree is a tree of int and int, and then being able to say for that tree, I want to create a branch with etc. of those. Now, another key question, inline function definitions. We're going back and forth. What I decided, at least to see, this definition definition is empty. I was originally showing you a bit different code here. Is not inlined into client code. We're not making that available. But it works anyway, which is good. Trade-offs are basically exposing implementation versus optimization opportunities. Really, for something this simple, I probably do want to inline it rather than pay for a function call. I was more curious to see if I could not do that. The other thing was being able to export function objects. So I have here the breadth visitor, which is a inline struct. It's a struct breadth, which I declare as an inline variable, breadth underscore, and then exporting a lambda which hands tree the breadth instance of breadth struct in order to visit it. Visual Studio disagreed that I had to export the breadth object. I think I do. This may be a case where it's, yes, some things are visible that you don't have to, without you having exported them. So breadth is a lambda, and the struct is then reachable. And the code basically just works. I had a fairly extensive test suite for this, which was useful, and then going through and basically um, uh, going through and exporting the things that the tests needed in order to be able to then pass the tests. Since the tests are modeling the actual code that I used, then my actual code just compiled and worked. Having test coverage is really good for this. It helps you not fool yourself about whether something needs to be exported or not. The compiler just tells you more. And that pretty much sums things up. Thank you for listening with me. Thanks for putting up with the audio problems. Okay, we've got a few questions here. No, okay, the private module fragment always goes at the end. You don't have a public section after that. You should be able always to organize things, however, because anything that you're exporting, you would have had to have mentioned name already, and then you just need to you're providing definitions at the end, or things that you're not using except within your private module fragment. Now, does Pre-build depending scanning requires serialization before main compilation, just per module for whole build. Okay, we can extensively parallelize the scanning um, with by deferring a little bit of work in building the graph. Essentially, what we need to do for any particular translation unit we need to know what modules it depends on and if it produces any module. And then we can plug that together, um, those nodes and edges together into the graph. We don't need to wait to scan any deeper than its immediate dependencies. Uh, uh, there are, of course, open issues in terms of packaging, in terms of how do you define, how do you get this information for something that's external to your project? It probably just ends up being added um, to your scan list, since you will probably need to build the the interface unit from source in any case. Okay, so I guess it sounds like we're pretty much done here. Thank you again for listening to me and giving me the opportunity to talk about this. Hopefully, this was useful. Um, I will try to be available around on GatherTown later. Um, Only challenge I run into with that is it's currently blocked on my company VPN. So I have to remember to get off the VPN to get onto that, or jump to a different laptop. Um, but I will probably be wandering the maze trying to solve that puzzle.